Good morning, class. This is Mr. Roberts at Shasta High School. Today we continue our discussion of modeling area and perimeter using algebra tiles. And we're going to pivot today because, to be honest, drawing a lot of algebra tiles is extremely inefficient. So we'll look at a better way, perhaps, to model products of polynomials using something called a generic area model. Just a real quick review of yesterday. We have these things called algebra tiles that allow us to visualize certain algebraic elements that we see a lot. For example, we can have these squared tiles. The dimensions of the squared tiles are each side is both x units long. So when we've got an x and an x, when we multiply it, we get an area of x squared. That's why this is called an x squared. So as important as the name is, it's also important to realize that there's dimensions for each of these, right? 1 times x is an x tile. 1 times y gives me a y tile. This tiles y units by y units. That's why this is called y squared. This tile is x units tall and y units wide. It's xy. And then we've got our unit tile. And pretty much any time that you would like to, you can jump to the CPM website and use their collection of algebra tiles to model certain situations. For example, if I had a single x tile and a single x squared tile and a single x squared tile and 5 x tiles, 3, 4, 5, and I'm going to throw some unit tiles on here as well. 1, 2, 3, 4, and then 5, and then 6. Not every collection of algebra tiles you can't create a rectangle out of every collection, but if you can, it turns out that although the order could be slightly different, the dimensions will not be, right? The dimensions will be the same. So I could, for example, have the x tile here. I could put a couple over here as two, so I can make this look different. But at the end, no matter what I do, I'm going to have the two dimensions. One of them is x plus 3, and the other one is x plus 2. And that's the only thing that's possible. So again, the dimensions here, this is x units long. Right? Yes, it's called x squared, but the dimension is x units long, and these are all 1 unit long, 1, 1, 1. So this is x plus 3 along the bottom, and then this is x plus 2 along the top. And as we said yesterday, there's two ways that we can write down the area of this collection. One of them is just by looking at the dimensions. Again, the dimensions were x plus 3, and the other dimension was x plus 2. And we can write the area as a product of those dimensions. So x plus 2 times x plus 3. But of course, equivalent to that product is the sum of the individual pieces. And if I would look at these, I see that I have a single x squared tile. There are a total of 5 x tiles, and there are a total of 6 unit tiles. So the important idea is that these are equivalent to each other. If I multiply x plus 2 by x plus 3, I do get x squared plus 5x plus 6. When I look at something that is not a rectangle, one of the things that we should be able to do is figure out both the area and the perimeter based on the dimensions of algebra tiles. The only tricky bit is that sometimes part of the perimeter is like this little piece right here added with this little piece right here. And if I think about it, this entire dimension is x units long, but that's being covered up by 2 unit tiles. So this is x minus 2. What's x minus 2? This piece and this piece together. The rest of it's pretty straightforward. This tile is a y, I've got a 1, this is x, etc. So if you could pause the video and go ahead and write down both the area and the perimeter. So I think if we add up the tiles together, we should have gotten that the area, we had a single xy tile, there were 2 y tiles, there were 2 x tiles, and then there were 2 units. And as far as perimeter, if I simplify this, there were Part of it is these little tiny bits together down here, which is x minus 2. But we had 12 units going around. There were twice when y showed up here and here. And there is a single x by itself here, but then there's another x locked up in this. So if I was to simplify that, we should have gotten that the perimeter was 2x plus 2y, and then just 10 units, because the 12 minus 2 gives me 10 on the perimeter. This is the last one of these that I want in your notes as a reference, and past this we will only use generic area models. But I want you to sketch this and then calculate both the area and the perimeter. Well, actually not the perimeter. That's pretty trivial. What I want you to give me is the area two ways. The area is the product of the dimensions, and the area is the sum of the pieces. So on the side that's off to the left here, we have 4 unit tiles followed by an x tile. So this dimension is x plus 4. And then along the bottom, we have a y tile, an x tile, and 2 unit tiles. So the dimension there is y plus x plus 2. And when I go through and I look at each of these pieces, I can see there's an x y tile, there's an x squared tile, there's 4 y tiles, 6 x tiles, etc. So the other way that I can write the product, this is the length times width, but I can also write it as the sum of the individual pieces. So the area is also xy plus 4y plus x squared plus 6x plus 8. And there's some convention on how we write the order, but as long as we have these terms, your product is correct, right? I'm not real picky right now about the order that we write these in. Addition is commutative. 2 plus 3 is the same thing as 3 plus 2. So at this point, algebra tiles get ridiculous and they're incredibly inefficient. So we will stop writing down things like this. What we would do instead is we would look along the dimensions and we would just come up with something we're going to call a generic area model. So what I've drawn here is equivalent to these two are equivalent to each other. So if you take a look at it, there's along the top down here there's 2 x's and then there's 3 1's. So you can see here I've got 2x and 3. Along the bottom I've got 1, 2, 3, 4 x's and 1, 2, 3, 4, 5. So this divides this rectangle up into 4 distinct regions, and if I want to find the area of each of the regions, I'm simply looking at the part of the rectangle right off to the left and below and multiplying them. So 2x times 4x gives me my 8x squared. 3 times 4x gives me my 12x. 3 times 5 gives me 15, and 2x times 5 gives me the 10x. So all of a sudden we have a much more efficient way to model multiplication of polynomials. To be honest, a lot of times I am not going to use area models like this unless it becomes like a binomial times a trinomial or trinomial times trinomial. But even in the case of just a binomial times a binomial, we could probably figure out these parts just by observing and noticing some patterns. Having said that, it's worth looking at the model. So the area of this piece, right, I've got a 5 off to the left and 2x below, so this is 10x. The area of this piece, right, there's an x off to the left and a 2x below, so this is 2x squared. In the upper right hand corner we have 3x, and in the lower corner there we would have 3 times 5, which is 15. So this is a quick way of modeling the following multiplication problem. If I have x plus 5 and I need to multiply that by 2x plus 3, the product of those two binomials is 2x squared plus 13x plus 15. And you can see I did combine my like terms, the 10x and the 3x, to get this product. Similarly here, this would just be the product of 3 times y plus 5. It's a nice way to model the distributive property, right? This is the simplest form of multiplying here, and definitely an area model is not needed, but the product is 3 times y and 3 times 5. So you can see that 3 times the quantity y plus 5 is 3y plus 15. When you get to binomial times trinomials, it's you're much less likely to make an error if you're using a model. 4y times 6y, 6 times 4 is the 24y squared. Negative 7 times 6 is negative 42y. Upper middle would be a negative 7x. Lower middle would be 4y times x, which would be 4xy. 4y times 1 is simply 4y. And positive 1 times negative 7 is negative 7. So expressed as the product, the area expressed as the product of length times width, I would probably write 4y minus 7, and then I would have the 6y plus an x plus a 1, and I would write that as, so you can see there's several times here where I've got some like terms, right? I've got the negative 42y, and combine that with the 4y. There is the negative, there's only one set of x's, right? There's just the negative 7x and the 7. So it looks like the only like terms I have are the 42, negative 42y and the positive 4y. So if I was to write this down as the sum of the parts, clearly I don't have all the parts visible here, but just combining like terms, I would have 24y squared. There's only 4xy's. There is a minus 7x. I did not leave enough room for this. When I combine negative 42y plus 4 more y, I get a negative 38y, and then there's the minus 7. So, of course, this should be written on one line, not spanning 2 lines like I did in such a goofy fashion. And then, of course, just multiplying x times 2x is 2x squared. 2x to the second power. 2x times another x. You can see x times x, 2 factors of x, 2x squared. So as we finish up our time today, I would like for you to just do these 6 problems in your classwork notebook area before you start the review preview. For each multiplication expression, I would like you to sketch an area model, label the dimensions and the area of each part. So you should have something that looks like this. And you'll notice that it was a 2 by 2, so I have, I've got the x plus 1 by the x plus 1, x squared, 2x, x, and 2. And then I want you to write an equation showing that the area is the product equals the area as a sum. So the area as a product is this part where it's the x plus y part. I'm sorry, the x plus 2 times x plus 1. So you're showing the 2 dimensions, this dimension times this dimension. And then the area as a product equals the area as a sum. Here's the area as a sum of parts. So go ahead and complete those exercises through F in your notebook, and you can move on to review preview then.